if you were not here yesterday, here's your handouts. But a student walks around in front of a motion detector that records their velocity at 1 second intervals. So this right here is recorded from a motion detector recording a student's movement. The movements are occurring for 36 seconds. She stores the data in her graphing calculator and uses it to generate the time velocity graph shown below. Describe her motion as a function of time by reading the velocity graph. So again, what did they just tell you? What is this a graph of?
It's a velocity graph.
Yes, it's a velocity graph that's showing her motion. So it's hard because you're reading a velocity graph, yet I'm asking you to describe motion. So this is where you have to be able to take that nice, lovely chart I keep telling you to memorize and use it to help you work through this problem. So again, as you're working through this, now maybe instead of F, F prime, and F double prime, you're thinking position, velocity, and acceleration. So what do we know about this chart? What are the first three here?
Increasing, decreasing, and then either 0 or...
The zero part goes there.
It goes by... What's
So
next?
if it's increasing
Extrema.
to decreasing, then they have to go to a max or a min. The max or the min is the 0 or the does not exist. If something's not 0, then it is what?
Positive.
Exactly. So then this goes here. So it goes increase, decrease, extrema. This repeats here. And then, how do we describe the original function? So this graph is velocity. Describe the motion from the velocity. The velocity is from here to here, positive. If velocity is positive, her position was increasing.
Increasing up until like 3.5.
This is 36 seconds. So careful. What are each of these tick marks actually going to have to represent? If this is from 0 to 36, how many tick marks are there?
4 seconds. Looks like it's 9.
Yep, so 4 seconds. So if there's 9 tick marks, 4-second intervals. So then
14 seconds. It's
4, 8, yeah, 12, 14.
Gradual.
So from 0 to 14, the position is increasing. So her motion would be going in which direction? Forwards or backwards? If the position is increasing, is she going forwards or backwards? Forwards. So the position is increasing, therefore the student is walking forwards. From 14 to, what do you think?
28. 26.
Yeah, probably 26. From 14 to 26, the graph is negative, therefore the student is what? Yeah. That was very bad, 14. what happens again from 26 to like, I don't know, 31-ish? 30?
Zero.
Yeah, the velocity is 0. So if the velocity is 0, what's she doing?
She's still. She's chilling.
Standing still. Good. So I'd say like 26 to 32. So it'd be kind of like being in a car and you're being stopped at a red light or at a stop sign. For that time period, your velocity is 0 when you're not moving in your vehicle. Granted, we're not ever taking your vehicle backwards, hopefully, on a main road, but you can kind of relate her motion to that of a vehicle. Then what happens from 32 to the end?
She's increasing forward.
Yeah, it's a positive velocity. Her position is increasing. So we could just go ahead over here and at 32 to 36, back is moving forward. Only because I ran out of room down here. Does that make sense? Can we understand now the relationship between the velocity to the position in terms of movement of a person? It says, when is her speed? And that's a key word in this kind of question. When is her speed a maximum?
21.
So, like down here, you're saying?
Yeah.
How do we know that's the maximum speed, even though on my graph it's a minimum?
The absolute values.
Exactly. Absolute value of velocity is speed. So what we have to do is we kind of have to imagine this being flipped up here, and this would be the highest point above, even though it's the lowest point below. So because speed is the absolute value of velocity, her speed's going to be a maximum at that 21 seconds. Is she moving forward or backward at that point? Backwards. Probably almost falling. Like kind of catching herself. Any questions on this? So we actually did example 1 already because we kind of went out of order because I wanted to have time to go over that graph with you. So let's jump over to example 2. Hopefully at this point is your example 2, the t squared minus 4t plus 3 on the next page. Okay. So, find the displacement of the particle. So again, yesterday we kind of had like a discussion about that, and I just want to clarify, like again, displacement is the position at that time. And then the distance will be the absolute value of those displacements. And find the displacement of the particle during the first 2 seconds. So go ahead, use your given function, and find the displacement of that particle. Displacement is going to be final minus initial. So it's not enough to just say S of 2. We have to do S of 2 minus S of 0. Because we have to take into account that this particle started at 3. So again, displacement is going to be final minus initial, where it's the final position at 2 seconds, subtracting away the initial at 0. So S of 2 would be 2 squared minus 4 times 2 plus 3 minus 0 squared minus 4 times 0 plus 3. So we get 4 minus 8, because again, assume no calculator. 4 minus 8 plus 3 minus 3. So those cancel. And we get negative 4. So it says t is measured in seconds and s is measured in meters. So that means the position at 2 seconds is -4 meters. So what does that mean in terms of direction about this particle? Yeah, it's moving backwards at this moment, right? So if it's -4 meters, that means it's 4 meters to the left of 0, which is actually going to be like 7 meters to the left of the initial. Yes? The symbol? So when I do displacement, oftentimes like I would write it as delta S, so change in position. Yeah. So it would be like delta S equals S of 2 minus S of 0, where distance is absolute value of S, or delta S.
So we're not putting it over the interval, like before we did like the initial time minus, like we're not doing it over 2, and we're just -4 meters is our answer.
Yes.
Okay.
Because we're not averaging this. That would be the average rate of change.
Okay, and so how would you do averaging?
So if I wanted the average rate of change, like it would say it would say average velocity right now, then it would be the S of 2 minus 0 all over 2 minus 0. So you would divide that -4 in half.
Okay.
So the average velocity would be -2 meters per second.
Okay. Gotcha.
Yes. Okay, velocity is just the derivative of position. So velocity would be v of t equals 2t minus 4. And I sometimes like when I find my velocities or my acceleration formulas, I throw my units next to it, because then if I have to find the velocity or the acceleration later, I've already done the math and thought about the units and I don't forget to write them. So when I found my velocity function, I said, okay, it's the derivative of position. Position was meters with respect to seconds, so this is meters per second. Then part C, what is the velocity after 3 seconds? What is the velocity after 4? So again, it's asking for instantaneous. It's not asking for average, it's asking for instantaneous, because it's saying after 3 seconds, what is the velocity? So what we're going to do is we're going to find v of 3 and v of 4. So we get 2 meters per second and we get 4 meters per second. So again, what you were kind of asking about was the average velocity. So if we wanted to know average velocity, the average velocity after 4 seconds would have been,
1.
well, average velocity would have looked like S of 4 minus S of 0 all over 4 minus 0. So that's the difference. The average velocity takes into account the position with respect to the time. So average velocity would be that delta S over delta T, where the delta S is your displacement. Different from instantaneous. These are the instantaneous velocities. How about your acceleration? If velocity is 2t minus 4, what's the acceleration going to be? 2. Acceleration ends up being a constant. So if they asked you to find the acceleration at 4 seconds,
15.
it's not changing. It's going to be 2 meters per second squared, whether we're at 4 seconds, 10 seconds, 30 seconds, etc. some key pieces of information that we want to know is when is the particle at rest? So the particle is at rest. Yeah. Go ahead. At 2 seconds, right? Because what happens at 2 seconds? The velocity is 0. So particle is at rest when velocity is 0. Particle is at rest when velocity is at 0. So again, those of you that aren't in physics, these are kind of like the things you don't quite know the same as like if you were in physics. So particle is at rest when velocity is 0. That should make sense in terms of this chart again. When did we say she was standing still? When it was flatlined on the graph, right? So the velocity on that graph was 0 because she wasn't moving. When does the particle move to the left and when does it move to the right? So how could we figure out direction of a particle? What do I need to take into account?
When velocity is negative or positive.
Perfect. So what I want to do is I want to make what I call a little sign chart comparing the velocity. So if we make a sign chart for velocity, we know at 2 seconds the velocity is 0, right? So what's happening maybe at 1 second? That's going to give me an idea of what's happening from 0 to 2. And then I want to know what's happening from 2 and above. Because if velocity is only 0 once, the particle can only be changing direction once. So what's the velocity at 1? Positive or negative? Negative. So if the velocity at 1 is negative, then the position is going what direction?
Oh yeah, left.
Good. Particle. I like did it right. So again, if velocity is less than 0, the particle is going left. Or moving backwards, depending on if we're talking about direction. What about at 3 seconds? What's the velocity at 3 seconds? We already found this, right? And then the velocity at 4 seconds. So those are both positive. Therefore, the velocity is greater than 0. Therefore, the particle is good. So it's going to the left from 0 to 2. It's going to the right from 2 to infinity, essentially, because we don't have an endpoint for this. Let's graph them. Let's graph them. Honestly, what graph's the easiest graph to do first?
Acceleration.
Yeah, because acceleration is a...
Well, it's just 2.
So here we are at 2. Hey, he answered a question today and was correct
It's a joke.
when
It's a
no one
fun
else
game.
answered. So his brain's still working in there. Maybe not as good as normal, but it's working.
Not a soul.
Ouch, that was harsh.
No, it's not horse.
All right, what is velocity 0? What is velocity 0? We just talked about it. So what do we know about the velocity? It's going to be right here at 2, 0, right? What did we say the velocity was at 3 and 4? Yeah, 2 and 4, right? So when velocity is 3, we're at 2, so we know we have the point 3, 2. And we know we have the point 4, 4. So I have 3 dots. I can at least kind of see a slope from this. We're going up 2 over 1. Does that make sense? Because our equation is 2t minus 4.
Yeah.
So that means the y-intercept over here is
-4.
good. connect those lines.
What does that mean whenever it intersects?
So
Is that like-
we're going to talk about that. No, it's good. That means that we can talk about speeding up and slowing down. So when they intersect, the particle is changing from speeding up to slowing down. So if velocity is, yes, but it has more to do with positive and negative. So when the velocity is negative and the acceleration is positive, then the particle is slowing down. When the acceleration is positive and the velocity is positive, then it's speeding up, and then the max speeding up or slowing down will occur kind of at those points of intersection. But that's what we're gonna get into that. Don't stress that. We'll get there. Okay. What do we know about position? What do we know about position? We found at least 1 point on there, right? We know S of 2 is
-1.
going at -4.
-4, yeah.
Oh, my bad.
Okay.
You really had me. I was like,
Where's
wait.
my mind with that right now?
S of 2 was at -4. Were we given a y-intercept? What's the y-intercept of a quadratic? 3, because it's the plus c value at the end of the quadratic in standard
how
form.
would it be? Oh wait, are you talking about displacement or disposition?
Position.
Would it be?
Oh yeah, because it's S of. You could be. Because it's a -1 because that was the displacement at S of 4. So like we have to go back. I only want this value. So I have to add back the 3 to it, which is -1. Thank you. So this is. So this is 1, 2. How'd you copy that one so quick? 1, 2, 1, 2, 3, 4. So again, this is kind of like your axis of symmetry. So you go 1, 2 that way, and get your other point at 3.
No zeros.
Or you could find them by factoring if you wanted.
Right there.
Just like it.
You don't have the equation, you just know the zeros.
So I knew in my head that this went up 1, 2, 3, 4. So the 1. So I knew this was up 1, 1, 1, 1.
Then it goes up 5.
I mean, I've been teaching quadratics for a long time.
Jeez.
And that's pretty much all we do in Algebra 2 for like 6 weeks.
You serious?
That's when we did our catapults. And you tried to cheat and steal the catapults
No.
from minions.
No.
Yeah.
I remember my
Oh, yeah.
Itself was first discovered centuries ago, pretty much. The discovery of calculus was concerned initially with velocity and acceleration, particularly with Newton and free-falling objects under that force of gravity. The description of this type of motion has captured the imagination of many scientists, including Aristotle, Galileo, and Newton. The investigations revealed that the distance a body released from rest falls freely is proportional to the square amount of time it has fallen. So again, that's where you get that position equals 1/2 gt squared in the basis of your equations. So position equals 1/2 gt squared came from this concept of an object being released from free fall and falling freely.
Write that one down. I missed it. 1/2 GT squared.
Correct.
You do the physics.
If a ball is given a push, then it has an initial velocity. So when you kick a ball or you push a ball to a child, you are giving it its initial velocity. In this case, we're saying it has an initial velocity of 5 meters per second. It is going down an inclined plane. Then the distance it has rolled after t seconds can be given by the following equation, 5t plus 3t squared. Find the velocity after 2 seconds. So once again, what are we doing to find velocity?
Taking the derivative.
Yeah, taking the derivative of position. What is the velocity at 2 seconds? Well, it's the derivative at 2 seconds. Or 17 meters per second. How long does it take for the velocity to reach 35 meters per second? So what's the idea happening in part B? If I want it to be 35 meters per second, where am I utilizing that in this formula?
30 of 35. We're all right.
So it's 5
Yeah,
plus
technically,
6t equals
definitely straight
35. Subtract away your 5, so you get 6t equals 30. Look, it's like not right. It was like not writing.
Sometimes it just doesn't want to write. Hurts.
So then you get t equals 5 seconds. So what that means at 5 seconds is the velocity is 35 meters per second. How high does the rock go?
2.
How high does it go? So again, new problem, new example, new words. I know, I just kind of, I asked the question. I asked the question
We were
without
talking about a
reading.
ball, now it's a rock.
So this dynamite blast propels a heavy rock straight up. It launches it at 160 feet per second.
Straight up?
Straight up. It reaches a height of 160t minus 16t squared. How high does it go? How do you find max height? There's 2 things we could do, right? We know something from algebra and we know something from calc. So Lynn, go ahead, you're up first.
You can find both the zeros and then find the midpoint of that and then
So that's the algebra 2 way, right? Find the zeros, and then what's that called? What's the midpoint of the zeros called? It has a special name. What? It's on the vertex. AOS, the axis of symmetry, is going to be that midpoint. But yes, the vertex, because the vertex is going to be the values. Okay, that's the algebra 2 way. That's the hard way. That's the hard way. What are you thinking, Michael?
When velocity is 0.
Exactly. Let's do it the calc way, guys. Velocity is going to be way simpler than trying to find the zeros of the height, then find the midpoint of the height. If we find the velocity and we find the zeros of velocity, we can find our height. You actually could have just found the vertex to the algebra 2 way by doing negative b divided by 2a. That's what I thought you were going to tell me. So velocity becomes 160 minus 32t. The zeros of this become 160 divided by 32.
I don't know what that is.
It's like
It's gonna be like
5, 5, 5, 5. It's
Tis.
5. Because 5 times 3 is 150, and 5 times 2 is 10. 150 and 10 is 160. Okay? So 5 seconds is the time at which it occurs. It's not the height. The height will be at 5 seconds. So now, exactly, I need to find S of 5. So 160 times 5, 500, 300. So you have 800 minus 25 times 6.
Is it 400?
It should be 400.
That's what I was thinking.
400 what?
Meters. Oh, yeah.
Feet. Jason.
I forgot the units, okay?
Jason, you don't walk with meters. You walk with feet.
Okay, same problem. Let's look at part B. What is the velocity and speed of the rock when it is 256 feet above the ground
Yes.
on the way up and on the way down? So remember, it changes. So what do we have to do for this problem?
256.
What am I setting equal to 256? Because I have two functions now.
Velocity
equation.
What?
Position. Oh,
So you're saying position, you're saying velocity.
I bet velocity.
Define the times, the two different times it takes to
Just
The
got
two
to say.
different times for velocity. See that equation?
Yeah, you could do that actually.
Yeah.
Oh, that's
So
kind of
guys,
like a P.
It is going to be position, right? The 256 represents the height of the object. We want to know what time is the object at the height. And then we're going to use that time to find the velocity. So again, you have to know what equation you're plugging into. So really, these are all divisible by 16. Because again, assume no calculator.
Oh.
You have to assume. I would take out even a negative 16. I'll make
Yeah.
factoring easier for
I'll
you.
do some oops.
I didn't know
What?
So again, if you divide this by negative 16, you get t squared. Divide this by negative 16, you get negative 10. Negative 256 is 16 squared, right? So if you take a negative out, you get the positive 16. Now you can definitely factor that. So factors of 16 that sum to negative 10. Awesome. So that means the times these are occurring. Yep. So which one's the way up and which one's the way down?
2 is the up. 8 is the down.
Okay, so we need V of 2 and we need V of 8. Are V of 2 and V of 8 going to be different or the same? The same with different signs. So all you have to do is plug in 2. So you have 32 times 2 is 64. 160 minus 64 is?
96.
So on the way up, velocity would be? On the way down, velocity would be? And the units are feet per second. We have one more question. It says, what is the speed? So how does speed compare?
Speed is just yeah.
Up and down.
Yeah,
Exactly.
Direction is not better.
Let's just finish. There's 2 more questions about the rock, and then they'll probably call you down to him time.
And you get that
Home
from
time
the
IQ.
spice.
Yeah. Let me see how many of you are you all leaving? Who's
No.
staying? Woo! 1, 2, 3, 4. It's the party! I'll give you your homework and we'll go over all homework tomorrow. Okay, what's the acceleration? Real quick, guys.
32 meters in the square. Negative.
What?
Good job.
You said that super out of order. Okay? So if the acceleration is a constant, when does the rock hit the ground? How would we find when the rock hits the ground?
Never.
What do you have to do? The rock's gonna hit the ground when?
Position and wait equal to 0.
Exactly. The rock will hit the ground when position function equals 0. Where did the rock start?
0.
So S of 0 is 0. So we gotta find the other time when this is equal to 0. This isn't that hard because once again, you can factor out a 16, leaving you 10t minus, actually you can factor out t too.
1 second. 10.
So the other time will be 10. So this is the initial blast, this is when it hits the ground.